Hello and welcome to today's IoT Central Workshop. My name is Andrea Riquetta and I'm head of the Pro Customer Success Team in Arduino. And I'm glad to welcome you, Jenny Plunkett from Gimples. Hi, Jenny.
Hi.
Would you like to introduce yourself?
Sure. Hi, I'm Jenny Plunkett, and I'm a senior developer relations engineer at Edge Impulse, and I'm happy to be here today.
That's great. So for today, the agenda will cover an introduction of Arduino, an overview of the boards that will be used by Jenny, and then we will start the workshop, and then at the end, we will have a Q&A session. Few notes, you should have received requirements and preparation note that mailed last days, but there will be a link in the notes below. If you want, you can submit question during the webinar and in the question box, and we will manage them through the webinar at the end of the Q&A session. So before we begin, 3 announcements. 2 winners will be picked up at random to receive a one-on-one hour with an Edge Impulse engineer at the end of the workshop. The certificates of the workshop will be mailed next week, and you will also receive details to how to view on-demand version in the upcoming days to provide you continued reference. Okay, so let's start. I'm going to share my screen. Okay. Okay. So let's start. I'll give you a short introduction to Arduino. So the mission of Arduino is to enable anyone to innovate and making complex technologies simple and open to use. We have offices in all around the world. Our headquarters are in Switzerland. We have R&D teams in Italy, either for the hardware and the software. We have a dedicated R&D for education in Sweden and the customer support as well. And then we have sales offices in US and in Australia. Arduino is organized into 3 business units that are aligned with the market. So everything starts on the education side, where the learn by doing is done for classes and teachers. So we provide custom products dedicated for schools, for teachers, and then we move to the maker business unit that it's to innovate and find creative solutions for everyday challenges. This is the long-last maker community we set up 15 years ago, and it's really huge. And then we have the Pro business unit where we want to enable business transformation. So leveraging all the knowledge that people can take by lessons and on our forums with the support. We want to leverage this and let the customers and the companies to start their business transformation. Our manufacturing, so our boards are 100% assembled in Italy. We have OEMs with several SMT lines. We have high quality standards and individual testing products. And we have dedicated suppliers for the Pro products. The Arduino Pro strategy is to provide the complete journey to the customer. So from the learning to the prototyping and production. For each of the stage, we have separate tracks. We have documentation. We have products that you can use for prototyping and validate your ideas. And then you can also move with the same hardware to production. So there's no change during the whole path, starting from the idea and then validating, and then going to the market. So it means that you have a really short time to market by using our boards. We provide a complete life cycle management for all the devices. We provided not only hardware, but we provide software tools that are needed for a smooth transition from the idea to the production. So today we will talk about the Portenta H7. Jenny will provide you some great examples on how to use this. The Portenta H7 is our most powerful and advanced board. It's dual core. It has a dual core microcontroller featuring M7 and N4. It's based on ARM embedded operating system. It has 8 gigabytes of RAM and 16 gigabytes of flash. Then we have a secure element. In this case is the microchip ECC 608 that provides security from the ground. So every connected product in Arduino has its own secure element that you can leverage to provide security from the ground, and so you can be sure that your data are safe. Then we have ADCs and DACs, 2 per 12 bits. And regarding connection connectors, we have the standard NKR form factor, and we also provide 2 high-density connector that expose 160 pins. For use cases, you can use Portenta when the performance is key. So we see some example today, but of course it's dedicated for high-end machinery, industrial machinery, computer vision, robotics controller, mission critical devices, edge AI. For this board, we partnered with great partners. So of course, Edge Impulse to unleash the capabilities of the AI and the machine learning. Then we have Lauterbach that provides a free Trace32 debugger for each board, so you can claim your license for free. And then OpenMV that provides an out-of-the-box experience when it comes to MicroPython program capabilities, so you can also program the board in MicroPython. So we have this IDE that is fully oriented to vision and MicroPython. The Vision Shield, it's a shield that is connected to the Portenta H7 through the high-density connectors. It has a camera sensor that it's capable of 320 by 320 pixels, support QVGA at 60 frames per second. It has a low power consumption. The board carries the Ethernet connector. It has also JTAG connector for debug capabilities and an SD card. The board it's also available with LoRa connectivity. The use cases for the Vision Shield, of course, are around all about the vision and the microphone. So we can do AOI, so automated optical inspection. We can have people and object counting, anomalies detection, and beamforming application, audio application. So we can use a microphone to train and recognize events. Okay, so that's for my site. You can start your journey with Arduino Pro at arduino.cc/pro. You can get more information on the Portenta H7 and the Vision Shield. You can write us for any kind of needs you have through the form at Arduino Pro arduino.cc/pro/contact us. Okay, so Jenny, I will give you the stage.
Great.
Okay, the stage is yours.
Awesome. If my producer can throw me over the presentation option, that'd be great. And also, he pasted a link in the chat. This link is to a GitHub repo that if everyone can go ahead and download while we're going through my little bits of slides, that would be awesome. If you know how to use Git, you can just clone it to your computer locally as you normally would. If you don't have Git installed, you can go on this page, click on this code button here, and you can download it as a zip. and then download that to your computer and then unzip it, and then we'll go on to the slides. Or you can just follow along and not do anything locally. That'll work as well, because this repo will remain public for you to access in the future. Before I get into the workshop, I just wanted to do a few slides. Let me see here. I just want to sort of set the stage of, what is Edge AI, in case anybody doesn't know. How is it involved with the Arduino PRO, and where does it come into industrial use cases? So what exactly is Edge Impulse? How do I collect a high quality data set for Edge AI or embedded machine learning applications? How do I design and train a highly accurate model? How do I deploy this back to my Edge device or my Arduino PRO? And then we'll do the workshop. So I'll just go through these slides relatively quickly, just so we can get into the fun stuff of going through the studio and making our machine learning model. But Edge Impulse is the leading embedded ML platform. From collecting your data set to designing and training your machine learning model, testing and validating your model for real life applications, and finally deploying onto your device, Edge Impulse is the leading platform for all of this. From end to end, we handle the entire process. But first step is to collect your data. How do you collect a really highly robust data set? Well, to even start thinking about collecting this data, we need to know what our use case is. So embedded ML can be applied to almost anything as long as you have high resolution sensor data. I have a few examples here. I have examples of use cases for recognizing sounds from audio. There's a cat speaking into a microphone. You could use embedded machine learning to recognize when your cat is meowing. That's one of the use cases there. You could classify images as a cat in this photo or as they're not a cat in this photo. You could do biosignal analysis with embedded machine learning. You could recognize sleep patterns and sleep quality from ECG signals or heart rate. You can also detect anomalies in things like accelerometer data for if your washing machine is about to break. Accelerometer data with embedded machine learning can help you do that. You can also even do object detection, detecting what types of objects are in field of view of your camera. And soon we'll be actually releasing object detection for microcontrollers. Right now, object detection is limited to Linux or Raspberry Pi devices. Soon we'll be able to run even on the PRO. So anything with really high quality, messy, high resolution sensor data is applicable for embedded machine learning. And I also just wanted to point out, feel free to ask questions throughout this workshop. I'm going to take it sort of informally, so happy to answer anything along the way. Answer any of your questions along the way. So in terms of Edge Impulse, in terms of our industrial use cases, we sort of go towards three main verticals. We have predictive maintenance, which is motion, current, audio, and camera types of sensors. And these can be done in things like factories to determine, if there's a person that's not at their workstation, we can do that with embedded machine learning. We can use current data to detect when a home appliance is about to fail or any other type of appliance as well. For asset tracking and monitoring, this is really important for packages and pallets, for example. We could use machine learning to determine when a package has fallen off of a pallet and things like that, because that can help determine good quality. And then finally, we also are looking at human interfaces for things like gesture and recognition and facial recognition. That can be done with embedded machine learning. We can also look at health data and recognizing when someone has a high quality of sleep or not high quality level of sleep. So these are the three main industrial verticals that we're looking at. And within these verticals, there's an insane amount of different things you can do with embedded machine learning. If you can think it, and if you have the sensor data, we can probably apply embedded machine learning to it. So your first step is select your sensor. Today, we'll be looking at audio, microphone data, and images from a camera, in this case, the Hymex camera on the Arduino PRO. But you can also use almost any other sensor as long as it has high resolution data. So things like accelerometers, temperature, humidity, air quality, ECG signals, camera, or for images and video data, water levels, light intensity, Doppler radar. The list is almost endless. If you can buy a sensor for it on any website, you can most likely apply machine learning to it. So your first step will be to collect these data samples. Edge Impulse makes it really easy for you to collect this high resolution data directly through the Edge Impulse Studio. So if you have an Arduino PRO or any other application or a smartphone, you can directly connect it to Edge Impulse and start taking labeled data samples and uploading them into your project. By labeled, I mean, is this an apple or is this an orange? And today we'll be specifically looking at things like cookies. Are they broken? Are they intact? We'll be taking pictures of these and uploading them labeled directly into the studio so we can start building and training our machine learning model. So like I was saying, image classification, this is just one sort of use case we could look at. You could use a camera for image classification. In this case on the right, we're looking at, is an egg cracked or intact? This is something that you could have on the assembly line in your factory to help determine food quality. And there's a whole bunch of other things we can do here as well. Forest fire detection is something that we're seeing, especially in Southern California and places where fires are happening all the time. A camera could be left in the field to help detect when a fire is happening or about to start. You could train a model to say, hey, it looks like a fire is happening, and more quickly alert first responders to come to the field. So object detection, this is something where you could say, hey, that's a bottle of soap, and that's a bottle of toothpaste, or that's a toothpaste, or that's a toothbrush. Object detection is awesome for real-time identification of objects in your field. So this is great for animal identification or determining if we're looking at a human or an animal just via edge machine learning. Gesture recognition is also pretty interesting. Using accelerometer data, I've also done this with Doppler radar data, where you can do gesture recognition just from embedded machine learning from the incoming sensor data on the device. So you could analyze whether a person is about to fall just based on the accelerometer data and inferencing with embedded machine learning. You would also do exercise detection, where you could say the user is doing a jumping jack or walking or running, also with the accelerometer data on your device. And finally, audio keyword spotting. This is what most of us think of when we're thinking of embedded machine learning, because we're thinking about Google and Siri and all these things where we want to talk to our devices. This is also all embedded machine learning. And this is great for home automation, where I could say a keyword and have the device do something. We can also see this on the Portenta example. When we're looking at our glass breaking use case, we could have a device set up where it's waiting to listen for a certain event, in which case, in this case, a glass breaking event, and we can alert our user to say, hey, a break-in is happening. We hear this glass breaking event. Come through and come take a look. Or you could do things like my cat is meowing a certain way, and that's also audio keyword spotting as well. So now that we know what our use cases are, now we know what we can do with embedded machine learning, how do we actually design and train your embedded machine learning model, or what we call the TinyML development cycle? So from model to device to cloud, first you need your raw data, where you extract these meaningful features. We need to extract meaningful features using digital signal processing algorithms because we want to give the machine learning algorithm less amounts of data to train on. If we're just picking the most important piece of these data streams, then our machine learning algorithm will not have to work as hard, meaning the resulting model will be smaller, which is best for microcontrollers that are really small and have small processing power. So we extract those meaningful features with digital signal processing. We train our model on those important extracted features. And then using that trained model, we then transform it into a C++ or Arduino library. And then we sample new raw sensor data that the model has never seen before, pass it into a signal processing function, run the inference or run our machine learning algorithm to analyze what's happening. We could take an example of the glass breaking use case. Taking that raw incoming audio data, analyze when we are hearing when we're hearing a glass breaking, or if we're just hearing background noise. That's what I mean when I say run inference. Then you're going to collect your conclusion. Every single time it hears a glass is breaking, it's going to send something to the cloud, or it's going to send something over the Ethernet vision board to your dashboard and alert someone to come check it out. This first step, though, collecting this raw data, extracting these meaningful features, doing the signal processing, training your model. This part is relatively hard right now. You need to have a lot of code to do the TensorFlow training of your model. You need to have a really large, robust data set up front, or even just start thinking about what you want to do with machine learning. So this part is really, really hard. And this is where Edge Impulse comes in. So the Impulse design page in the Edge Impulse Studio, which I'll go in much more depth during the workshop, is basically a graphical version of what you do in the Tiny development ML cycle. Tiny ML development cycle. So the first part is our raw data. In this case, we're looking at image data. So we're just going to normalize our images to be all black and white or all color, all at the same size, or if some are landscape or some are portrait, we're going to squish them down to all be square. Our next block is our digital signal processing block. This takes those raw images and transforms them again to either be black and white or color, or you can do any other signal processing you want on these images there as well. And then based on the extracted features that we get from the signal processing block, based on the most important pixels of each image, essentially, we send these to our machine learning algorithm. And this is our transfer learning block, which is based on TensorFlow and Keras in the Edge Impulse Studio. These are just blocks that are graphically represented, basically covering up little Python scripts. And the Python scripts are completely available for you to alter and edit on your own if you know how to write TensorFlow code. All of that is available for you to access. But if you don't know how to write TensorFlow code, the graphical version is available for you. So we have our input features, which is our digital signal processing extracted features from the previous block. And the output features is what we want the machine learning to do. In this case, in this screenshot, we're looking at of our raw images, of our raw incoming image data. We want to see which image is containing an apple, which images are containing an orange, and which are unknown. And then we output these and send the results of these conclusions to our cloud platform or other parts of our embedded application for things like home automation, etc. So now that we have our impulse designed, we have our model deployed to our device, or how do we actually deploy our model to our device? And this is where the Edge Impulse SDK comes in. So depending on your use case, there's a lot of different microcontrollers available for you to use. This is just today. As we'll see in the future, the constraints of different ML models are going to get even smaller or even larger. The constraints are going to not be as meaningful. But this image is essentially saying, hey, on a Cortex M0 Plus today, we can for sure do anomaly detection on accelerometer data and other basic sensor data like temperature and humidity, for example. But if you go just one class up to a Cortex M4, like on Arduino Nano 33 via Sense, today we can do voice, vocal keyword classification, different audio classification, and also accelerometer data classification as well. But even if you have the camera shield from the Harvard course, you can also do image classification on an Arduino Nano Cortex M4. So this graph is changing constantly, but this is essentially saying as you go up in different classes of devices, the more capability you can do with your machine learning model. All the way from a Cortex M0 doing accelerometer anomaly data classification, all the way up to video classification with a webcam on your Jetson Nano. And today we're looking at the Arduino PRO, Cortex M7, Portenta applications, which can do image classification, audio classification, and accelerometer classification today. But soon, Edge Impulse will be releasing a constrained object detection model that will be able to do object detection directly on the Portenta as well from the incoming video stream. So we have tons of different devices for you to use. In addition to a various amount of libraries that you can deploy from the Edge Impulse Studio, you can also directly deploy a pre-built firmware application, which is essentially a proof of concept application directly to your device from the studio. So the studio handles all the scripts for you, builds the application, bundles it all up into an SDK, and then makes a proof of concept application available for you to just drag and drop onto your device. Today, I'll have you guys all go to that GitHub website and directly download that firmware or that source code to your computer, and we'll build it on our own. And that's using the Arduino library you see on the right. But we also have the ability to deploy to a C++ library, and this includes all of the code that you need in order to get started building your embedded application with Edge AI. So this includes all of your TensorFlow code, all of your machine learning code, all of your digital signal processing code as well, and any other code that you wanted to include in there. All of that is available in the Edge Impulse SDK. It's completely open source, completely no black boxes. All the source code is given to you in these downloads. So how do I get started? Well, I'm going to show you in the workshop, but I just wanted to put these in here as well. If you're new to embedded machine learning and you really want to dive deep into what is actually happening, I recommend checking out our Coursera course that we helped develop with Sean Hemmel. That's available on the right here. He goes into great detail on how you can get started with embedded machine learning, especially if you only have a small background in embedded machine learning as well, or embedded devices in general. And then on the left, we have great documentation on our website for getting started. We have awesome tutorials, awesome blog posts, so I recommend checking that out on the left. And now let's get into the workshop. So like I said, feel free to ask questions as we go. I don't know if I actually see the questions now that I'm looking at it. Let me see. Well, let me pause presenting for a second. Okay, so just to point out, while we're working on getting these questions up, this was the prereq sheet that we sent out to you yesterday or the day before. Basically, hopefully, everyone who wants to follow on locally has installed the Arduino CLI, the Edge Impulse CLI, and has sort of started collecting their hardware. And if you want to follow on the food quality assurance use case, then you got like a cookie. If you can see my webcam, this is the cookie that I'm using today, and a smartphone. Oh, now I see the questions. Let me see. Okay. Where is the link to the GitHub? Here's the link to the GitHub. I don't have access to the chat window. Okay, thanks, got it. Okay. And by the way, this is the link to the GitHub. If you want to go ahead and already, you can download this, like I said, as a zip file, or you can clone it as you would any other GitHub repo if you know how to use Git. If you download a zip, just make sure you unzip it and then open that directory in your terminal application as so. Ooh, that's not what I want to do. Okay, let me see what other questions. The LoRa connection with Pretenta, is it only LoRa or is LoRa WAN? I think that LoRa question is a good one for Andrea, but there's also two different shields. There's the LoRa shield and also there's just an Ethernet shield as well. Is it possible to integrate the Arduino Pretenta with federated machine learning and connect the Arduino with other Arduinos and transfer some weights between them? Oh, that's an interesting question. Federated machine with the Edge Impulse SDK, I'm not sure if that would be possible, but what I'm going to say is please post that question on our forum, and I'd be happy to send it over to our machine learning engineers, and they can get the best answer for you. Let me see what other questions. We can't do object detection on the Pretenta though, right? Do I need a Raspberry Pi? As of today, with Edge Impulse, you need a Raspberry Pi or a Jetson Nano, but very, very soon, like really soon, we'll be releasing our updated object detection module, which includes the availability for you to do object detection on any MCU class device, including the Pretenta, and any one of our supported boards on our website that include camera adapters. So like the Sony's Presence, for example, as well. And you can check that out on our documentation. And I'll paste that in the chat.
Yeah, in the meantime, I can pick up a question from Alvaro that asks LoRa connection of the Portenta. It's only LoRa, or also LoRa 1 is supported. Yes, both LoRa and LoRa 1 are supported.
Another question is the ESP board supported? Not officially, but we do have a blog post from one of our user success engineers, David, who wrote up a great blog post on how you can use the ESP32 cam with Edge Impulse. So I recommend checking that out. I will send that in the chat. Sweet. Okay, I've seen that OpenMV is very used to develop CV models. Can that also be used OpenCV for developing the models? Well, if you're writing a Python script with Edge Impulse SDK, you can do whatever you want in Python. I've done an OpenCV with the Edge Impulse Python SDK as well. And I can show you on the deployment tab, we also have OpenMV libraries that you can directly build firmware for from image classification models as well. I'll send you that documentation. I'm going to send you the documentation to the OpenMV camera. Sweet, thank you guys so awesome for these are great questions so far. Feel free to keep asking them, but assuming everyone has downloaded the GitHub repo locally to their computer for ones that are following along as we go live. Sorry. I'm going to get right into it. The first example that we'll be looking at with the Arduino Portenta today is an audio use case. So the main two things that we're looking at with the Portenta today are using microphone data for embedded machine learning and the camera data for embedded machine learning. So today we'll be looking at a glass breaking use case. So analyzing when we hear glass breaking or when the device hears glass breaking, alerting our user to go and check it out. That's our first use case, and our second use case is food quality assurance. So using the camera on the Portenta to say, hey, this cookie is intact or this cookie is defective, and we need to push it off the assembly line or the factory line or anything else. And this can be done with any type of food item that's regular. You could even probably do it for bananas as well, as long as they're not as long as they're the same type of banana, I guess you could say. I also have two different types of cookies in this data set as well, but we'll discuss that more later on. So for the first use case, glass breaking, we're going to create a new Edge Impulse project, or you can go to the GitHub and clone the project directly to your account. So you log into the Edge Impulse Studio, and what you can do is, I'm going to send this link into the panelist chat, and you can clone this project, and that cloning this project basically takes all of the data from my project, all of the trained model information, and directly copies it into your Edge Impulse account for you to use. So if you go to this public page from the link that I think my producer can send to everyone that I just pasted into the chat, you click over to the top right here and click clone this project. Make sure you're logged in. I already am logged in, so I'm not sure why it's doing that. Maybe because it's my own project. Make sure you're logged in, clone this project, and then there'll be a button here that says clone to your account. And then we can get going. Because I'm assuming people don't have just glass available for them to break in their houses right now. But the Edge Impulse Studio is pretty cool. From the entirety of the TinyML development cycle from top to bottom, you basically just follow this side dashboard here from top to bottom, and that takes you all the way from connecting your device, collecting your data, training your model, testing and validating your model, and versioning your project, and finally deploying to your edge device. So the first tab here, dashboard, is the information about your project. It gives you all the information you need in order to start creating your first embedded machine learning model. It shows you information about how much data you've collected, And you also get access to all the intermediate TensorFlow data as well. If you know how to develop applications using TensorFlow, all of the intermediate artifacts that you would get from using TensorFlow as normal, you also get here to download as well. And then you can add your collaborators, as well as publishing a public version of your project as well, which is what I did from the link that was posted in the chat. Okay. The first thing we want to do, hopefully everybody followed the instructions from the prereqs and successfully connected their Portenta to the Edge Impulse Studio. If they haven't, please go through the prereq sheet here or ask me any questions. And after today, if you have any further questions, please feel free to ask on the forum at forum.edgeimpulse.com. So the devices today here, I didn't connect my device for this specific project because I'm using a pre-built data set for glass breaking analysis. And this data set is from a machine learning challenge from the DK.community 2017 challenge for rare sound events. So I've uploaded all this data into Edge Impulse, and you can go to the data acquisition tab and directly click on each one and hear what it sounds like. So in addition to all the glass breaking sounds, we have background data as well. You can see on the device, and that was my colleague David. So for a machine learning model, we want to make sure we have at least two different classes of data. And by classes, I mean labels of samples. So in this case, we have two samples, glass breaking and background data. So our glass break data is obviously all of our audio samples that include glass breaking noise. And our background data is data that will help our machine learning algorithm more easily determine what is a glass breaking sound versus what is just background people chatter or fan noises or factory noises, etc. So we've uploaded about 6 or 7 minutes of this data, 3.5 minutes each for background and glass breaking data. And we've done this for both our training data and our testing data. So we have about a 71%, 29% training and testing data split. And this is great because this will help make sure that our model is really well trained on lots of various types of data, and also make sure that our test data is pretty robust so we can make sure our model is going to perform well in real life applications. So we've done that for our training data and our test data.
Process would be
so just all the background data contains other types of human voices, factory noises, things like that. So this will make sure our machine learning algorithm is really, really precise in making sure we're actually going to be able to detect glass breaking. Okay, so we've uploaded all this data. Let's move on to designing our machine learning impulse or our machine learning algorithm. Sorry, excuse me. So if you clone this project directly from the link that was posted in the chat, then this will be already filled out for you, and you could technically just go straight to the deployment page. But let's pretend that we're just filling this out for the first time. So on the left, as I mentioned in the slides, this is the raw data block. This is the first step that we need to make sure that our audio is really clean, everything is all of the right size, of the right frequency as well, and basically just cleaning it up and making sure it's all uniform. You can downsample to a different frequency here in case you had audio data that was sampled at different frequencies. You can upload data from any source into Edge Impulse. It doesn't have to be from audio that's sampled off of the Portenta, even though you can do that. You can also upload data directly from your mobile phone. You can upload it directly from your computer or any other way as well. You can also use an API to pull microphone data from a Raspberry Pi. The options are pretty endless. And most of these microphones do record at different frequencies. So you want to be able to downsample to make sure your machine learning algorithm doesn't have to work too hard between different varying levels of resolutions of data. Our window size is essentially going to go over the different, basically take small 1000 millisecond windows of our samples and extract those meaningful features in 1000 millisecond bits or chunks. And then from those 1000 millisecond windows, we're going to then increase every 500 milliseconds to extract those features. And this will make much more sense when I go to the spectrogram tab next. And this is what the spectrogram tab will be doing. It will be using a Python script that we have pre-written for you in Edge Impulse, basically windowing over all of your audio data and extracting the most important key features, or in this case of your audio data, the most important peaks and valleys. We have a bunch of different processing blocks available for you to use in Edge Impulse, from analyzing human voice data, non-human voice data, processing image data, analyzing repetitive motion from things like accelerometers for gesture recognition. You can also use raw data just as it is if you want to do digital signal processing elsewhere. This just takes raw data without doing anything else to do it, and using all the features in that data, sending that into the machine learning algorithm rather than just extracting the most important ones. So today, because we're looking at non-human audio data, we're going to be using the spectrogram block. You could also take a look at what the MFCC and the MFE blocks would do as well. And then our neural network block here is also, again, this is a GUI wrapping over a Python snippet. This is where we're going to, from those extracted most meaningful features, we're going to run it through our machine learning algorithm, and we're going to determine, based on more incoming audio data, are we hearing a glass breaking noise, or are we just hearing background data? And then we have our output features, background and glass break. Based on the incoming raw audio data, if our machine learning has determined whether this incoming sample or this incoming window is classified as glass breaking noise or not. Let me see, is there any more questions? Is there a potential shield that comes with an IMU? I think Andrea can answer that one. I'm not sure off the top of my head. But moving on to the spectrogram. So all of the DSP blocks that are pre-written for you in Edge Impulse are just a graphical interface wrapping over a Python snippet. On all of our Python snippets for these digital signal processing blocks are available for you to view and download as open source from our GitHub repo as well. So if you want to see exactly what Python code that we're using to do the spectrogram block, you can see that in our GitHub repo. And if you're curious on that, I can find the link and send it to you in the chat as well. So basically what you see here is we have our 1000 millisecond window. And over this 1000 milliseconds, we're extracting all the raw features, and then from these raw features, processing them through the Python snippet that we have for the spectrogram block. And all of these parameters here on the left for the spectrogram block are inputs into the Python function. So different parameters into the Python function. So most of the time I just leave these as the default because we have a pretty good analysis of what needs to be done for each pre-written DSP block, but you're also able to edit these in whatever way you see fit. And then we click Save Parameters. And then we go to the Generate Features tab, and this takes all of our raw data, passes it through the Python snippet that I have for the spectrogram block, and outputs this 3D feature explorer here on the right. Let me make sure you guys can see it pretty well. So this feature explorer is essentially a 3D visualization of what our data looks like after it's been passed through the digital signal processing. So using the different various information we have from the data, the most meaningful features, we've mapped it onto this 3D visualization. Or we're basically using the UMAP algorithm here, a Python library, to make this visualization. But this visualization is awesome for when you're collecting and analyzing your new data in order to make sure it's all labeled correctly, because we can see we have a really good split between our background noises and our glass breaking sounds. If we notice that some of our glass breaking sounds are actually within the cluster of the background noises, that might mean that our glass breaking sound is not really that high quality, or it was accidentally mislabeled as a when it should be background noise. So this 3D Feature Explorer is really awesome for helping you make sure that your data is really high quality and really well labeled. Because if your data is not well labeled, your machine learning algorithm is not going to perform well in the end anyways. Looks like there's another question. Anomaly detection models can be developed in the Edge Impulse platform, for example, to detect anomaly motor vibration. Yes. If we go back to the design page, underneath the neural network Keras block, we also have a bunch of other pre-built, pre-written Python scripts using TensorFlow for you to use. In addition to the neural network Keras block or the classification block, we also have regression. And depending on what type of data you've uploaded into the data acquisition tab, you'll see other pre-written blocks available for you to choose here too. So you can do anomaly detection, image transfer learning, things like that. And sometimes there'll also be, depending on the data that you've uploaded, there will also be an object detection block here as well. So these blocks that are shown to you on this Impulse design page is highly dependent on what type of data you've uploaded to the data acquisition tab. We can see here on the food quality assurance. Then we can see we have other types. We have transfer learning. And if I opened up an accelerometer application, then I'd see anomaly detection as well. Great. Thanks for the question. Okay, so now that we've extracted our features, we have a really good separation between background noise, label, and glass breaking sounds. That means this means that our machine learning model is going to perform fairly well, just because we know our digital signal pre-processing is already doing it quite well and already separating them quite well. But we want to make sure our embedded machine learning is going to perform well too. And because we have our digital signal processing down so good, this should mean that our model is going to be quite accurate, which we see here on the right. So what I've done here is this is the neural network tab. Again, this is all just a GUI visualization of what we would do in a Python script with TensorFlow. So I have my number of training cycles here. I've set them to 100. I've set my learning rate. And this determines how fast the neural network will learn. And depending on the level that you set this at, it could overfit quite quickly, or you could have it not overfit as fast. We also have ability in here to do data augmentation. Depending on the type of data that you've uploaded, we can randomly transform your data to make sure that your model will not overfit and that it'll perform more like how it will in real life. So this is the default that I have here, my neural network. This is the default for this audio type of data that I've uploaded here. But if you know how to write TensorFlow code or Keras code, you can switch into expert mode. And you can see the exact Python code that was written to create this GUI visualization. So I can drag and drop different layers, different architecture layers. I can write my own Python code here. I can type whatever I want in here, and then all I have to do again in order to get this visualization on the right is click Start Training. So I don't know how to write TensorFlow code, so I'm going to switch into visual mode. I can see all my layers here. Click Start Training, which I've already done. And on the right, I can see my model's performance. Looks like it's about 95% accurate, because 95% of my training set, or the validation set that was separated from my training set, is correctly identified as background noise, and 96% of my training set is identified as glass break when it should actually be the glass break. On the bottom here, we can see the feature explorer that we just viewed from the digital signal pre-processing block. You can see a bunch of green and red dots down here. For all of the samples that I've uploaded into my data acquisition tab, the ones that were labeled as glass break and not glass break or background, you can see the ones that were correctly identified to be glass break and the ones that were incorrectly identified to be background. So we can click on each individual sample to see exactly which window this came from and from which sample. And this one was incorrectly identified to be background noise when it actually should be glass break. So we can listen to it. Oh, it looks like I need to retrain my model because I think I changed around some things in my data acquisition, so it's going to be a little different. We'll fix that, and I'll show you exactly what this looks like on the next application. But if I didn't mess around with my data acquisition tab, this would work and I'd be able to play exactly the sample after clicking on each individual dot here in the Feature Explorer. And on the bottom right, I can also view my on-device performance. In this case, we're predicting for Cortex M4F. And obviously, we're using a Cortex M7 today, so these on-device performance numbers are going to be much different. But I can see my inferencing time, or how long it takes to go from extracted feature from the digital signal processing block and getting this predicted output or predicted label. Is it glass break or is it a background noise? I can see how much peak RAM memory I can, how much peak RAM this is going to take in my Edge Impulse SDK on my device or in my proof of concept application. You can also see how much flash this neural network block will take as well. And it's relatively small. You can get it even smaller if you're using other types of architecture presets or neural network layers. And if you can even get it smaller if you're using a different digital signal processing block as well. And if you want to learn more information about that, feel free to post in our forum, and I'd be happy to send you over some information, especially from our digital signal processing engineer. He has a lot of information about this. Let me take up the questions as I pause here really quick. Is Edge Impulse free to use / open source for all users? Edge Impulse is free to use. Go ahead and sign up and get started building your own machine learning models. There are aspects of Edge Impulse that are enterprise only, but for everything that I'm showing you in this workshop today, you can do for free. I can also show you the enterprise features as well, if that's interests you and your company. But everything from in this studio, this project view, you can get started on your own today, whenever you'd like, for free. Is there an Arduino platform where the results of the model can be viewed in real time? I don't know if there's a GUI application for inferencing results. What I will do is I'll show you what it looks like when we flash this or deploy this to our device. The Edge Impulse SDK creates a proof of concept application for you that shows the results of your inferencing over the serial connection to your terminal. And I'll show you that in a moment. It's pretty cool. But you could also design your own GUI or web application that sends the results of your inferencing over Ethernet from the Portenta's Ethernet Vision Shield and create a little web module that shows your inference results as well. Let me see. So the Spectrum Feature Explorer, I see all background samples were labeled as deleted. This I think was my bad. I think what I did was something must have happened when I messed around with the data acquisition earlier today. But basically, in order to fix that, all we need to do is regenerate our features, and that should fix it. Just click Generate Features, and this will regenerate this page, and we'll have to retrain our model again. But this should help us to click on each individual sample in the Feature Explorer again. All right, just doing it pretty quickly. Cool. And then you can also see the on-device performance for the digital signal pre-processing block as well. This is calculating or predicting for Cortex M4F. But yeah, so once we've regenerated these features, now the Feature Explorer works. And if you're seeing that deleted sample issue on your own account, just do what I did. Go to the Generate Features tab, regenerate them, and then you should be good to go. And now we can go back to our neural network tab and retrain. And this one will take a little bit longer. Shouldn't take too long though. Okay, let's see. Do you recommend data augmentation? So data augmentation, I would say it really depends on your use case and the data that you've uploaded. I've seen data augmentation work really nicely, especially for keyword spotting use cases. We don't have it turned on for this case, but it also just depends on what you're developing for. And these are questions that we can definitely help you answer if you post them on the forum. We can help you determine the right course of action depending for your use case. Armand, did you regenerate your features on the spectrogram tab? Spectrogram. Cool. But and also to finish up that data augmentation question, feel free to turn it on, you know, see what it does, see how that affects your model performance, see how that affects the model testing page. I would say you can't really, you know, do wrong with just trying it out. But awesome, now that we've retrained our model, we can then see exactly every single background glass break data that was correctly and incorrectly identified by the machine learning model here. And we can click on the play button and listen to see exactly where that window from that sample came from. Oh, well, that definitely does sound like background noise. So, oh, glass break. Yep. Noise. Cool. Yeah, that kind of sounds like glass, doesn't it? So I can see why the machine learning algorithm got that one confused. Yeah, so you can zoom in here and see exactly which clusters of samples were misidentified as background or glass break. And you can do it even further. If you scroll down, go to the live classification or the model testing tab. If you click on the model testing tab, you can bulk classify all of the data that you've uploaded into your testing data tab and pass all of this test data that the model has never seen before into your trained model and spit out exactly what every single sample, what its label is predicted to be, and the percentage accuracy. Great. Glad to see you got it working, Armand. Thank you. Thanks for letting me know. So we're just classifying all of our test data. We're passing it through the digital signal processing block. We're getting those important and meaningful features, passing them through the trained model to get our predicted label. So we can see we have very similar results to our validation set from our training set that we see on the neural network tab. On the neural network tab, our accuracy was 94%, but on the model testing page, our accuracy is only 92%. So we lost a little bit of percentage accuracy in the real life application of this. So that might mean that we need to collect more data, or we need more background data, or we could just leave it at this because this is pretty good accuracy for our use case. How often are you going to be able to hear a glass break, for example? So this will work for us. And again, you can see exactly the digital signal processing features that were extracted from each individual sample, mapped into a 3D visualization. And you can see the green and red dots, which ones were predicted correctly and which ones were mispredicted. Now that we've done our model testing, we can move on to versioning. Say I really like the way my model is performing right now. I really like how it's at 94% accuracy. It's doing what I want for the use case that I have, especially for the environment that I'm putting my device in. So I'm going to save this. And what versioning does is takes all of my data at this current point in time, all the labels, all of the model parameters, all the digital signal processing blocks, all of the output, all of the intermediate model data, basically wraps that up into a zip file that I can then restore at any point in time by cloning into a new project. So this really makes iterating on your machine learning model really easy, and makes industrial use cases really nice as well, because say I want to make this just general model, but for this one factory, say one factory in Texas, but I take this model that I built for the Texas factory and I want to use it in Illinois. But the background noise in the Illinois factory is a lot different. So the model accuracy in Illinois is not as good as it is in Texas. I can version my project, clone it into a new one, and then add all of my new background noise from the Illinois factory, and now I have a new iterative model based on my previous data set. So I can store that version, and I can also make it public, so I can share it with my colleagues or send it on social media. This link, if I post it on Twitter, for example, I could have anyone in the world could clone into their own Edge Impulse account, get all that data, and get started working on their own projects as well using the data set that you collected. When you have a big model, is it possible to train this one on the Edge Impulse platform, or is there GPU limited? So for the majority of our users, we're not seeing people hit any compute time limits. So all the training in Edge Impulse is done in our cloud servers that we pay for. So Edge Impulse is free, but all of the training, all of the resources that we use in order to train your model are done on our instances or whatever we spin up for your job. So for some big projects, for object detection or image classification or really large audio projects, we do see people hitting the GPU compute time limit for Edge Impulse projects. But if you do see that limit, you'll get an error that says, please email us at hello@edgeimpulse.com. Please just email us, describe your use case, what company you work for, and we'd be happy to help, figure that out, either give you a trial of upping that compute time limit, increasing that GPU for you to train your model. But again, we see a majority of our users for at least early proof of concept applications never see this issue. So just keep that in mind. We don't see a lot, but email us at hello@edgeimpulse.com and I'd be happy to discuss that with you. So now that we've versioned our project, we've made end-to-end a machine learning application for our glass breaking anomaly detection. Let's deploy it to our Portenta. So hopefully everybody's downloaded the GitHub repo to their computer. And what we can do is I've already pre-compiled this exact version for us. So what you can do is you can follow the instructions to flash the pre-compiled firmware from this repo onto your Portenta. Or you can click Arduino library on the deployment tab, scroll down, and then click build. This will build an Arduino library that you can then import into your Arduino IDE, or you can just use the source code from the zip file that's created and use it as you would with any other Arduino CLI project. And that's what we're doing today with the Arduino CLI. If you scroll up, you'll notice a few interesting things. You'll also see build firmware. So soon, when we fully release for the Portenta, you'll see the Portenta here is an option to directly build a ready to flash proof of concept application, pre-built binary for you to flash. You don't see that today. That's why we're using the GitHub repo. But be on the lookout for that. We'll be releasing very soon. But say you have any other board. I know some people in the audience have an Arduino Nano 33 BLE Sense. If you have an Arduino Nano, you can click this button directly, and this makes you a pre-built proof of concept application that's ready for you to drag and drop and flash onto your board. So you can click on this icon, scroll down, click build, and this will create that binary that you can directly flash. And then when you have the Edge Impulse CLI, which we'll do in a moment, then you can follow along. We also have this special Edge Impulse Eon compiler. So TensorFlow has their own compiler that they use for TensorFlow Lite applications for microcontrollers, but we've taken that one step further and made Edge Impulse applications even smaller, the SDK even smaller, at least 50% smaller, depending on the type of data that you've uploaded into your project. So you can see here that the RAM and flash usage is about 10K and 87K with the Eon compiler. If we don't use the Eon compiler, it goes up from 10K RAM to 11K RAM, and it goes up from 87K flash to 105K flash. So memory is really important, especially for small microcontroller applications with medium range processing power. So we want to make sure we have all the memory that we can get. So the Eon compiler is great for that. You can also select between int8 or float32 quantization as well. Okay, so for people who have the Portenta and they have the GitHub repo, I'm just going to go assume that you've already downloaded it to your computer and you are CD'd into the directory. If you want, go ahead and use the pre-compiled version of the firmware for the glass breaking example, and you can find that there under flashing the pre-compiled firmware. CD into the glass breaking folder, CD pre-compiled, glass breaking, and then there's a command here with the Arduino CLI that finds your Portenta if you plugged it into your computer and flashes the firmware in this directory onto your board. So I'm going to do that here really quick. And we've hit the hour mark, so I'm going to do this quickly, and then we'll move on to the image classification use case. So now that we flash onto the Portenta, we're going to use the Edge Impulse CLI now to run our inferencing of our proof of concept application directly on the Portenta and start classifying new audio data. Edge Impulse, let me make sure you guys can see it. Edge Impulse, run impulse -- continuous. And this allows us to inference continuous audio rather than just small chunks of 2 seconds, 2 seconds, 2 seconds, which is not as useful for like keyword spotting or glass breaking spotting. So Edge Impulse run impulse continuous. This is sending the results of our inferencing from our Edge Impulse SDK directly from the proof of concept application into our serial terminal. And these X's over here represent the percentage of accuracy of what the model thinks it's hearing. So it's sort of getting it wrong right now in that it's finding some small percentages of what it thinks it might be glass breaking noises, but for the most part, it's getting background correct. So let me open up the Studio tab here, and because I do not have any glass to break in real life, what I'm going to do is I'm going to go to the Data Acquisition tab, and I'm going to play a glass breaking sound from the data acquisition that we uploaded, and we should be able to see 100%, 10 out of 10 X's for the glass breaking column here on our serial terminal output. There we go. So now the Arduino Portenta has correctly identified that glass breaking has occurred, and from those inferencing results right here, you could send a notification over to your cloud application to alert someone in the factory that someone's trying to break in, or anything else you want to do with that inferencing result. I could do it again to show you. Let me do a different glass break sample. So great, it's correctly identified that it heard the glass break. And this is processing continuous audio data directly from the microphone on the Portenta, using the trained model that we use in Edge Impulse and sending the results of these inferencing over serial connection to our computer and the terminal. And that is audio inferencing with the Arduino Portenta H7. So now I'm going to stop this and we're going to move on to our image classification use case. And we're going to do it fairly quickly because I know we're running out of time. I want to make sure we have time for a solid Q&A session. Let me pull this back up. I've lost my chat window. Okay, here it is. Okay. Again, if you have any questions, feel free to ask them in the chat. Cool. So the image classification for the Arduino Portenta, the process is almost identical to what we did for the glass breaking use case. But instead, we're going to be doing image data and different signal processing blocks and a different neural network block. But the flow in the Edge Impulse Studio is almost identical. So I'm going to paste this link, and my producer can send that out to everyone. So this data set will be interesting because you probably don't have the same exact cookie that I have, but what you can do is using the Edge Impulse daemon, you can connect your Portenta directly to your project and take images of a cookie, or something that's in your house and upload it directly to your project. I don't have necessarily time to help everyone through that today, but what I'm going to do is I'm going to send a documentation website of how you can start collecting data. Send the image classification tutorial. And this tutorial will go through all of the options of what you can do to upload new data to your project. In this case, in this project, I've uploaded data of images of cookies that I've taken directly from my phone, actually. The Edge Impulse Studio has a web GUI that you can take pictures directly with the camera on your phone, upload them into your Edge Impulse project, and you can build a machine learning model using pictures that you've taken from your phone and use these images to build a model that you'll then use on the Portenta. So it's awesome. The Edge Impulse Studio is awesome. You can use data from any source. It doesn't have to be images that you've taken using the Portenta camera. You can upload pictures directly from your phone and use them to inference using the camera on the Portenta. So I have about 343 images of various cookies. I have intact cookies, ones that are good, and we want to make sure that those stay on the assembly line for packaging, and ones that are defective. So cookies that are broken in some way, or ones that have been taken a bite out of, or ones that have a crack through the middle. These are defective or broken cookies. So I have all of this for my training data set and my test data set. So you'll want to have a bunch of pictures that are taken at different angles with different lighting. Really, we want different backgrounds, or a background that is more representative of what we'd see in the factory. My tables are white, so that's why they have a white background. But for the cookies that you have in your environment, go ahead and take about 400 pictures of intact and defective cookies and upload them into your Edge Impulse project, or clone the one that I have, and you can see exactly what this looks like when we follow along together. To answer some questions, what kind of audio sensor data was used for the glass breaking case? So the audio sensor that was used for the glass breaking case, at least for the glass breaking noises, I'm actually not sure what sensor source these glass breaking data samples were from, because I downloaded them from the rare use case sounds data set. I can send you this link in the chat. You can read more about it in the 2017 challenge. There might describe the source of the glass breaking sounds for you there. But that's a good point you bring up. You usually want to, for audio data, it depends. If you want super high accuracy, you want to use an audio source for your training that's similar to the one that you'll be using in the real life application. So usually I'd want, the Portenta microphone to have recorded the audio if I want to use it really in production. But as we saw, the accuracy just from data that I've uploaded from other sources to train my model, using the microphone for new raw data on the Portenta was actually really fairly accurate as well. So it just depends on your use case and how level of accurate you need to be, the level of accuracy you need to have. Also, can the Raspberry Pi 4 be used alongside Edge Impulse for deployment? Yes, we also have information for that as well. Edge Impulse for Linux. Send that in the chat. Or let me send the Raspberry Pi 4. Okay. So moving on. Now we're running out of time. Let's see. Image. So yeah. So now that we've uploaded all of our images of intact and defective cookies, and this is awesome for our assembly line, because we want to make sure that no one gets shipped a cookie with a bite out of it. So moving on to our impulse design. Again, almost identical looking to the audio use case, but instead we're just looking at image data. So we're resizing our images, making sure that they're all square, choosing how we want to resize them. Some of my images might be portraits, some might be landscapes. We want to squish them or crop them in a way that will make them all uniform. Our image signal preprocessing block here will take all of our images and translate them from RGB into black and white. The camera on the Portenta is actually a black and white only camera. But that doesn't mean you need to have black and white images as your training data. You can upload color images and then have the digital signal pre-processing block in Edge Impulse translate them to black and white automatically for you. And then you can train your model in those black and white images, and it'll work really great for the Portenta. And then again, we have a bunch of different processing blocks available for you to use here. Obviously, for image classification, we're going to do the image pre-processing block. For transfer learning, we're also going to do this transfer learning is what we're going to do for image classification, but you also have the ability to do classification and regression as well. Just depends on what you want to do for your use case. And then our output features, again, are defective versus intact. So our image pre-processing block, this is where we're taking this color image of our cookie, taking those raw features of the hex values of each pixel in the image and making it into grayscale. We could also have RGB depending on the type of camera that we're using to deploy on our edge device. But because we're using the Portenta, we're going to switch it to grayscale. And these process features get spit out, and these are what we're going to be using to pass into our machine learning algorithm. We can also see the on-device performance here, and this is predicted for a Cortex M7, which is closer to what the Portenta is. And it only takes 4 milliseconds to get from these raw features into these processed features and in a grayscale format. And it only takes 4 kilobytes of RAM. So this portion, this digital signal processing block, the code that is included in your Edge Impulse SDK from the deployment tab is really quick and pretty small. So we're going to generate these features, and we have a pretty good separation. We can see some great clustering in the Feature Explorer here. We can click on each individual sample and see pictures of our cookies, which ones are intact, which ones are broken or defective. As you can see, the name as we scroll over in this Feature Explorer, it's actually showing the name of the sample file name rather than its label. So as you can see, these are labeled broken, but then I decided to switch and to make the label named defective instead, so it's a little bit confusing. But intact and broken or defective. And then again, we can, see which ones are maybe mislabeled or these images are not really very good quality. Like this one kind of looks intact to me, but obviously it is broken. So we might want to, add more pictures to our data set to even further clarify this separation in our digital signal pre-processing block. So now that we've gotten our features, it's pretty good for my use case. We're going to move on to transfer learning. And transfer learning, again, we have pre-written Python blocks for you, pre-written Python code here for you to use. We have a bunch of different types of mobile nets for you to choose from. And these mobile nets primarily just change depending on the resolution of data that you want for your machine learning algorithm and how much memory you have available on your device. If you're using a Jetson Nano, you can go all the way up here and use, 683K of RAM. But because I'm on an MCU and I really just want it to be as fast and as small as possible, I've chosen the MobileNet V1. But we have a bunch of mobile nets here for you to use. And then again, if you know how to write TensorFlow code, you can switch into expert mode and see exactly what Python code is written for this mobile net. It's quite interesting, actually. We also have data augmentation here for every image. We can resize, sort of randomly transform things, and really emulate exactly what the real life image application will be doing, like on the factory floor. So I'm going to switch back into visual mode. Sorry, I'm going to mute 1 second. I'm a little bit sick. Okay. Party managed to flash the glass break out there into the Nano 33 and it worked on new sounds. Awesome. Glad to hear it, Armand. Awesome. You can also deploy things directly to your mobile phone as well. If you don't want to spend time flashing things to a microcontroller, I'll send a link to that in the chat as well. It's actually really cool. Edge Impulse has a lot of different ways you can really quickly prototype applications that you want to use for your real life production applications or use cases. So there's that. Okay, so we know how to write transfer learning code in Python. We're going to switch back into visual mode. We're using our smallest MobileNet V1 in this case because I just wanted it as quick as possible. I'm sure you could use a different MobileNet for the Propenta just because it is such a beefy microcontroller, but I'm just keeping it simple today. And I can see exactly, you know, my accuracy isn't really that great, but for this example, it's gonna do fine. So I have a 94% percentage accuracy for my defective labels or my defective images that I've uploaded into my training set, and 84% accuracy for my intact. So intact is not as good accuracy as my defective ones. So what we need to do there is we need to upload a lot more data. More data usually means better accuracy and different various lighting levels, various backgrounds, and that will really enhance our accuracy there. But again, this works for my use case today. Sweet. So moving on to the on-device performance, we can also see estimating for Cortex M7 how much inferencing time this will take to get from extracted features from the digital signal processing block into the inference result, or classifying it as an intact or broken cookie. We can also predict how much RAM and how much flash this processing block, this neural network block will take as well. It's quite big compared to the audio example, but that's to be expected because image data is quite more high resolution than just small audio samples. So, and again, this will change depending on which MobileNet you've chosen. So it's really important. If you have a microcontroller that's even smaller, like the Arduino Nano, you need to make sure you're choosing a small MobileNet, or else it's not even going to flash onto the board. Okay, so now that we've done our transfer learning, we've trained our model, we have decent accuracy for our use case, let's move on and go to the model testing tab. So we're just going to go through, classify all of our test data, exactly what we did for the audio use case, and see which ones of our test data were classified correctly as intact versus defective. So we have really good accuracy here compared to the transfer learning accuracy that was shown. This might be because of a few things. The data that we have uploaded in our test data might be more similar to the data that we've uploaded to our training set, meaning that there might be some samples in our training set that are just really way off different compared to what we have uploaded to our test set. There's a lot of different things here. The best thing to do, again, is to just upload more data. We can see our feature explorer. It looks a little different than our other DSP block because, again, these images are probably more similar looking to each other than what we uploaded to the training set. And if anybody is uploading their own data, let me know if you're figuring out how to do that based on the links that I sent you. And I'd love to see if you have cookies at home of your own cookies, seeing what level of accuracy turned out for you. I'd love to see it, so feel free to send it over or shoot us a tweet or post in our forum. I'd love to see. Okay, so we've tested our model. It's looking great for our test set, but now let's figure out how it's performing in real life on our Propenta. And again, we can also version our project. You can see here I have 3 different versions for the workshop. And again, this is the same type of versioning that we did for the audio. Bundle it all up to a zip file, and you can clone and go back to that point in time whenever you want. So I recommend doing that as well, especially if you're adding a new label or a new type of cookie. That's really good to do. Moving on to the deployment tab. Again, because we're using my GitHub repo that I've sent to everyone today, we're going to click the Arduino library to create a library, and then we're going to build and extract those source files and paste them into our firmware that we're going to build with the Arduino CLI. But if you have a Arduino Nano that has a image board, an image shield on it, then click on the Arduino Nano 33BLE sense picture, and this builds a pre-built proof of concept application that you can directly drag and drop onto your Arduino Nano and get started doing image classification without having to write any code. So that's really cool. But today we're going to choose the Arduino library, click build, download that zip file, and extract them into our workshop repo. So I've downloaded the zip, I'm gonna extract it, downloads, good quality source, go into source and select the Edge Impulse SDK, model parameters, TF Lite model, copy these folders, go into our workshop repo directory, click on the source folder and delete Edge Impulse SDK, model parameters, and TF Lite model. Delete them, paste them into this folder, go back, and all this information is in the GitHub repo README as well. But then we're going to create a library from this Arduino export, sh source / Edge Impulse SDK. Oh, wrong directory. sh source Edge Impulse SDK, create library. And this just makes sure all the files that we've deployed are properly situated for our Arduino CLI. And then we're going to do /Arduino build.sh -- build. And this will take quite a bit of time, but thankfully I have already uploaded a precompiled firmware for us to use. So we're going to cd back into today's workshop repo. Workshop, precompiled, food quality. And then we're going to copy and paste that command for the Arduino CLI from the repo. And this will flash over what we previously uploaded for the glass breaking use case and flash onto our Portenta. Erase. All right, and now all we have to do in order to start inferencing on incoming image data from the Portenta's vision shield is do edge -impulse -run impulse. We're not going to do -- continuous this time because we're not going to do continuous inferencing on image data. And now we can, using the camera, hold it over your cookie and determine if the cookie is intact or broken. And I'm holding it over an intact cookie right now. You can see this one, and if you can see my webcam, it is correctly identifying it as intact. As you can see right here, the prediction is over 8.8, which means it's really confident that that's an intact cookie. Now I'm holding it over a broken cookie. And it's taking a moment here. There we go. Now it's correctly identifying it as broken. And that is doing image classification using the Arduino Portenta H7 Vision Shields camera and doing machine learning on the edge with incoming image data. And very soon you'll be able to use the Portenta to do constrained object detection as well. And using this sort of same flow, analyze objects in your environment, recognize if you're looking at a human or an animal, all with Edge Impulse as well. So keep on the lookout for that in our blog. And this was the workshop. Let me see what other questions are in the chat. Okay. When you build, what does it mean about the OpenMV library? When is it suitable to use? So if you go to our documentation, we actually have a officially supported board called the OpenMV CAM H7 Plus. This OpenMV CAM uses Python, it uses a Python IDE. So the OpenMV library export option is specifically for this supported board, but feel free to deploy it and give it a go. If there's a way you can use it on the Portenta, let us know. I'd be happy to, see that and help debug that with you, especially on our forum. But that's essentially what that's for. It's for our OpenMV Camera H7 Plus official supported board. Let me see what else here. Before deploying the algorithm in the Arduino, is it necessary to install some dependencies, or is the program to auto-run the model in Arduino? Okay, so I didn't go through the build here because it takes forever, but essentially, yeah, it's still building. But essentially what the script is doing, I'll show you here in GitHub. What the Arduino build script is doing is it's downloading all the dependencies that you need in order to build for the Arduino Portenta using the Arduino CLI. So it needs certain things like the embed core, it needs other things, but you can view exactly what's being downloaded from the dependency script in the Arduino-build.sh file. So it looks like we download the embed Portenta core, MKRW WAN, and then it includes all of the files from the Arduino library export from the deployment tab that we used, all the TensorFlow code, all the digital signal preprocessing code. And then so /Arduino build.sh /build just builds in the project for you. But we can also do, if you're just using the main folder instead of using the precompiled option, you can do /Arduino build.sh --flash, and that script will flash it to your board for you as well. But all that is included in the README from the GitHub. If we want to visualize the classification or the boxing and labeling of objects, how can we do that? So that's a great question. Let me see here. Our CTO, Jan, has created a great example where he has created sort of like a visualizer for object detection applications via a web application. And I do not know the link to that off the top of my head, but let me write that down and I will send that over to David and he can send that in an email to you guys as a follow-up to this workshop. So let me write that down really quick. Visualize. Okay. When is a good reason or scenario to use C++ or other languages provided? And, you know, it just depends on how you want to build your model or how you want to build your application on the embedded side of things. The majority of our users do use C++ library export option if they're doing hardcore, you know, embedded development for a board that's not necessarily officially supported by Edge Impulse. If it is officially supported by Edge Impulse, you can just build the proof of concept binary down here, and that makes it really easily. But again, all of these proof of concept firmwares are using the C++ library export to build. And all of these example proof of concept applications are available in our Edge Impulse GitHub for you to use. They're all open source. And you can see exactly how that C++ library it is to take in all that DSP code, all that neural network code, and build a binary for your specific board. So it just depends on your use case and depends on the board. Again, for a lot of Arduino boards, you'll want to click on the Arduino library because that's just the easiest way. Okay, Arduino CLI upload, you didn't have our embed Portenta installed. So what you'll need to do is run /Arduino build.sh build from the main directory, and that will install all of the prerequisites and required files for you. I didn't think about that when I just said use the Arduino CLI to flash, so that's a good point. If you just installed the Arduino CLI and you've never used the Portenta before, then you wouldn't have had the dependency, so apologies for that. But just follow through the README from top to bottom instead of just compiling or instead of just flashing the pre-compiled firmware, and you'll get all those dependencies from the Arduino build script. Is it not necessary to work with the Arduino software? We are using the Arduino software. We're just using the Arduino CLI. But you can do exactly what we did today with the Arduino IDE as well. Do you know some microcontroller that comes with a built-in night vision camera? I don't off the top of my head, but I will say if you can find a great night vision camera on any site, like any vendor like DigiKey or something, I'm sure you can find a way to plug it into a microcontroller and get that data off of there and sort of build your own dev board that way as well. But I would just search Google night controller with night vision camera and see what comes up. And then if you find that board, then you can build an application using Edge Impulse with that night vision data and just deploy as a C++ library. And you'll have to integrate with your drivers on your own, but it's relatively trivial if you know how to write embedded code. But if you have any struggles with that, please post in our forum and we'd be happy to help debug with you. About bounding boxes. About bounding boxes, and they link to the object detection. With the data collected, we need to label this data. Click on the labeling queue, no labeling queue, okay. Armand, did you have a question about the bounding boxes? I think I've gotten through all the questions. Let me see, okay. The link you were looking for, oh. Oh, so yeah, so the labeling queue for object detection, the link that you're referring to, yes, that is one way to visualize your bounding boxes for sure. And in our object detection tutorial, we go through exactly how you can use the labeling queue to directly take your image data and visually and graphically draw your bounding boxes to get these objects labeled. But I think I was also referring to, I think the way I understood the question was after you've already labeled these and trained your object detection model, when you deploy, is there an example that has shown a good visualization of new incoming data in its bounding boxes, which Jan has made. He's made like a web application for it, but I'll find that and I'll send it to you. But yes, this is also another way to visualize your bounding boxes. Getting a compiler error in the Arduino IDE related to the OV7675. Do you recommend building through the CLI? So if you're using the OV7675 with the Arduino Nano 33 BLE, I would just say just deploy the pre-built firmware that we have right here. That will make a proof of concept application for you for the OV7675. I think it's the OV7675. I'd have to look. But yeah, so I would do that. But then yeah, make sure you're deploying this Arduino library, and then we have a documentation tutorial for that specifically. Let me find it. Let's see. Yep. Yeah. Yep. Let me see where the instructions are for that. Oh, running your locally Arduino. Yeah. So then you can follow this documentation. If you want to use the Arduino library deployment option instead of using the proof of concept pre-built application for the Arduino Nano 33, you can follow this tutorial to import the Arduino library into your Arduino IDE, and then open up an example sketch from the Arduino menu. And you can use an example sketch from the library that you imported to flash onto your board, if you'd rather do it that way rather than using the precompiled one from the studio. I think I sent the link in the chat. If my producer wants to send it out to everybody. Great, thank you. Just a statement here, a grayscale OLED is very useful with Vertenta. Ooh, that sounds fun. Jeremy, do you have a tutorial for that by chance? That'd be awesome. Be an awesome way to visualize exactly what your Vertenta is seeing as well. Because it can sort of be hard, to sort of exactly see what's in frame. unless you have some sort of like serial web GUI happening. The upload of the deployed model can be done by USB and by Wi-Fi. So for the Pretenta, you could definitely upload. You could do some sort of over-the-air update over Ethernet. I don't have an example application for you to do that, but I'm sure someone in here has heard of something like that before. Actually, does this Wi-Fi? I think it does. But yeah, so the upload of the deployed model that we built from our GitHub repo, that's done over USB, the flashing at least, in this example. But I'm sure there's other ways that you can also upload your firmware over the Pretenta, and I'm sure Arduino has lots of robust documentation for that on their website. But yeah, once you've built that firmware, that binary, the hex file, mat file, you have everything you need in order to send your firmware any way you want, especially if you know how to do over-the-air updates. That's what you could use as well.
Yeah, I can add something on this. Yes, I can say that on the cloud side of Arduino, we can deploy OTA. So basically, you can compile the file, the inference, the binary, and then you can deploy to the board.
Great. And I'm sure you have a documentation for that somewhere.
Yeah.
And yeah, I think we just have 15 minutes left. So everyone get your last questions in, and I really appreciate it. These have been great questions today. I've really enjoyed it. The OpenMV provides an option for real-time vision preview. Yeah, the OpenMV board is really cool. I recommend checking that out. The OpenMV application is quite interesting as well. But as I didn't actually show, one of the things you can do, let me actually pause. One of the things Edge Impulse can do in our pre-built firmware is do live preview of the Pretenta camera in the data acquisition tab. So let me do that really quick. I'm pausing because I'm logged into my production account and blah, blah, blah. Pretenta. And this is what I'm doing right now is you can't see it, but I'm logging in through the CLI and connecting my Pretenta to my Edge Impulse project over the Edge Impulse daemon. So I'm replaying. So I've done that here. So I've done edge-impulse-daemon. I've named my device Pretenta. I'm going to go to the data acquisition tab. And now I can see a live preview of what my camera feed is seeing from the Pretenta. Like I'm sort of zooming in on the, so yeah, so hi. So that's also an awesome way for you to take new images. So I could say, I can go over my cookie here, label it intact, and then I can click start sampling. And now I've just directly taken a new image from my Pretenta itself, and I can see exactly what was in field of view camera. And this is using the Edge Impulse CLI. And all of this data from the camera is being sent over the serial connection from the USB cable. So that's another cool way. Let me go back to the questions. Let's see. Can we get a link to the Coursera course? Yes, you can. Let me grab that. Yay, GlassML works in your Pretenta. Awesome. Oh, thanks, Jeremy. Yeah, so I think I sent it over questions, but let me send it in the chat as well. Send. Sweet, yeah, and our colleague our colleague Sean Himmel created this course in collaboration with Edge Impulse, and it's a really awesome course to really help you understand exactly what's happening in embedded machine learning. So this takes you all the way from the intro what are neural networks, and you'll end with building a keyword spotting application like we did today with our glass breaking. And he's also just recently released another course, I think for computer vision. So then you can just go back on to do a cookie classifier for intact and defective cookies as well with Sean Himmel. Great. Yeah, let me just play around with the live preview. Does anybody have any last questions? And now we're heading towards the end here. Read Edge Impulse CLI. Deploying directly from the web page to connected device is not supported yet on Portenta H7 yet. It will be very soon. As you can see on the deployment tab, we don't have the Portenta H7 up there yet. Our embedded team is working out just a final few issues, but you can build whatever model you want and go to this workshop repo, copy and paste your deployed Arduino library over the ones in the source folder as I described in the README. And you can use whatever sensor data you want with the Portenta and build your firmware using the Edge Impulse SDK with this repo today. But soon, very soon, you'll see an icon for the Portenta H7 on the deployment page of the Edge Impulse Studio as well. Like really soon. It's gonna happen soon. Is there a way to add a microcontroller night vision processing capabilities? So what I would say there, just get a night vision camera and take night vision images, and then you can start inferencing on your night vision image data after you've trained your model on these specific night vision looking images. That's what I'm assuming you would do. I've not personally done it, but sounds like maybe Jeremy has. So what I would do is post in the forum, and I'd be happy to send some resources to you specifically about night vision applications. All right. Any other questions? Oh, looks like a new embed core came out today. Awesome.
Jenny,
yes.
I have a question. I have a question. It's something that happens a lot to me, and people are asking to me. Thinking about the data, so the model to be trained, from your experience, how big should be to have an efficient recognized model? So how many samples or there are differences between vibration sensors, image sensors, audio sensors. So how big should be the data set?
So yeah, it really depends. I mean, I've had a really good accuracy for my model from example, from an image data set that really was only like 100 images big. You can get really good accuracy for really small data sets, just depending on your use case or what you're actually trying to classify. And so I know that's like kind of like a cop-out answer, but it really just depends on your use case and what data you're uploading. For accelerometer data, you really don't need much. I've done maybe 1 minute to 2 minutes of accelerometer data before and gotten like 100% accuracy. But yeah, I know 400 images looks like a lot, but with all the different ways you can upload data into the Edge Impulse Studio, it's really not that many pictures. You can take pictures really, really quick, upload them, and it's really, and you can see these images are not that much different from each other. And we're still getting really good accuracy. So it can go really quick. You can really build a model that's really highly accurate in just a few minutes with this Edge Impulse Studio. So the long story short is it depends on your use case, but even small amounts of data can get really high accuracy. And with our machine learning engineers they're doing advancements in every single day in our product. So soon you won't need very much data at all to get awesome machine learning accuracy.
Great, thanks.
Start closing out of things. Let me see. Food quality algorithm works on the Nano 33. the ready to go feature works well. Does have some trouble with the TUC cookies? Great idea to bring cookies, by the way. Just ate half the package. I know. When I was taking pictures initially with these cookies, I literally ate like half the package. They're delicious. But awesome, yeah. So if you had some trouble with some types of cookies, then the answer to that is take more pictures, retrain, and you can easily retrain and extract your features from the DSP block by clicking on the Retrain Model tab and then click Train Model. This will go through all of the new data that you've uploaded, re-extract all those features, retrain your model, and then you can deploy again. This is assuming that you didn't change any parameters in any of your blocks. This is only assuming that you've uploaded new data. So that's a really easy way to do it. I'm glad you enjoyed your cookies. That's awesome. My students loaded the images with their cell phones super fast. Yeah. One of the things I didn't have enough time to go over today, but I sent the link out, is Edge Impulse has this really great feature where you can directly connect your mobile phone via QR code to the Edge Impulse project and take pictures directly from your camera without even having to save them, directly upload them to your project. And that's what I did in this case for the cookies. It was super, super quick. And yeah, hundreds of images in a matter of 10, 15 minutes, really not that big of an issue. And I followed this tutorial here to do that. And I'll send that again in the chat. And I think we also have 2 winners to announce for the one-on-one section with an Edge Impulse engineer. And those 2 people are Justin Lutz and Nishka Uberoy. I hope I'm pronouncing their names right. But congratulations, you guys. Thanks for coming to the workshop. I had a lot of fun. I hope you guys did too. And please post in the forum or email us if you have any further questions.
Okay, so some few notes. So the attendees will receive an email on details on how to view this workshop on demand on IoT Central, and the certificates will be sent out next week. And yeah, congratulations to the 2 guys that will have this one-on-one with the Edge Impulse engineer. So congratulations. Okay. Any other question?
Great, you guys had so many awesome questions. Thank you so much for coming. Email us, either Arduino email or the Edge Impulse email if you have any other questions. And yeah, let us know how it goes. And please tag us on social media if you make anything with the Vertenta and Edge Impulse. Oh, it looks like Jeremy would like you to chat about the Vertenta. Jeremy, did you have any specific questions? Oh, thanks, Christopher.
Great. Okay, so I think that we are at the end of this webinar. So thanks a lot, Jenny. Thanks to people that attended, and please visit iotcentral.io for more insight and events like this. I hope you enjoyed this webinar, and see you next time.
Bye. Thank you so much.
Thank you.